Now that we've seen translations, let's have a look at reflections. Here, we're going to start with reflections in the x-axis, which is also called the line y equals 0. That's your horizontal axis. Now, even though it's the horizontal axis we're reflecting in, the effect will be what we call a vertical reflection, which is to say that we'll be affecting the y coordinates of every single point on the graph. If those y coordinates are positive, they'll become negative. If they're negative, they'll become positive. And if they're 0, well, they'll remain unchanged. Maybe try to picture what this graph's image would look like after a reflection in the x-axis and draw it before you click through the animations. The graph of f of x equals x minus 3 squared is an upward facing or upward opening parabola. After reflecting in the x-axis, we now see that it's downward facing. If we look at a couple points, like 0 and 9, that point has now become 0 and negative 9, as the point 6 and 9 become 6 and negative 9. Again, the y coordinates are being multiplied by negative 1. But do notice that the vertex, which was at 3 and 0, is still at 3 and 0, because multiplying the height of 0 by negative 1 has no effect on it. This is an invariant point, but not because it is the vertex, but rather because it was on the x-axis. Any point that is on the axis of reflection will be invariant under that transformation. So we could say that a reflection in the x-axis makes all y coordinates negative, but we have to remember that if they started negative, they become positive. So it might be more helpful to say that they are all multiplied by negative 1. That's going to be shown in our replacement, which we'll see in a moment. Now the equation of g of x, written in terms of f of x, could be written as y equals negative f of x. We put the negative sign out front when we have a vertical reflection. This represents that the output value, or the entire height of the function, is multiplied by negative 1. So how would we actually change the equation in terms of x? Well, typically we would replace y with negative y, and then as a next step, we would have to multiply both sides through by negative 1. So what this effectively does is makes the entire right side of the equation become negative. Here we've shown that by putting a negative sign out in front of the bracket. Notice we will not distribute it in right now, because in the order of operations, the exponent takes priority over the multiplication. A great habit to develop is to check your work by putting the equation of the function into your graphing calculator. That way you can make sure that the graph you got is the same as the one from the question. Here we've shown our two inputs as well as the window settings. Here we'll look at another example of a reflection in the x-axis, but this time we'll work with a piecewise function. A piecewise function is basically a function made up of more than one function, or parts of functions, which is to say we won't be given a single equation for this to punch into our graphing calculator, and typically we'll only have the graph to work with. This isn't a problem for us, it just means we can't check our work as easily after. So here we're asked to sketch the image after reflecting the x-axis, to label the new graph, and specifically the 5 points that were indicated originally. So let's go ahead and do that. Notice that some of the points were originally below the x-axis. In fact, 4 of the 5 indicated ones. After the reflection in the x-axis, they are now above it, because their heights were multiplied by negative 1. The point that was found at 3 and positive 2 was the only indicated point that had a positive height, so it was reflected to 3 and negative 2. In each case, we did not change the x-coordinate, because this is a vertical transformation, and therefore only affects y. I also want to point out that these 5 points were all off of the axis of reflection. So we do actually have 2 invariant points in this question, but they were none of these points, which may sometimes be considered endpoints or vertices. The mapping rule that describes a reflection in the x-axis is written as xy becoming x and negative y. We've mentioned this, that the y-coordinate is multiplied by -1, and that's how the mapping rule shows it. So our two invariant points here are again located on the axis of reflection. In this case, the points 1 and 0 and 4 and 0 were our x-intercepts. X-intercepts will be the invariant points for a reflection in the x-axis. The reason x-intercepts are invariant in this transformation is because when we multiply 0 by -1, it does not change its value. This next exploration will ask us to work with the function y equals x squared minus 4x plus 5. We can tell from the x squared term that this is a quadratic function represented by a parabola. And what we're trying to show here is that in the second case, when we give y2, which is equal to negative bracketed x squared minus 4x plus 5, we have effectively multiplied the entire right side by -1. This is multiplying f of x, or the height, by -1, and is therefore the transformation of reflecting in the x-axis again. So let's have a look at how these two functions appear in our graph and see if we can compare the coordinates to their vertex to find the relationship between them. You'll notice here that because we were given the function in general form, we'll need to use either an algebraic strategy, such as completing the square, or a calculated function, such as second calc minimum, to find the vertex of the graph. Minimum because this is upward facing, so it's the lowest point. Here, you'll see that the minimum was calculated as 2.000012. The reason this is not exactly precise is just because of the estimating techniques that the calculator uses, but you can consider that to be exactly 2 and 1. We input y2 and find a similar situation where we will use second calc max, this time max, to find the vertex. Again, we notice that it does not give us a precise 2 and -1 here, but again, we can consider that to be exact. So now that we've got the two vertices, we may notice that in both cases the x-coordinate is 2, but the y-coordinate is 1 and -1, so the same value with opposite signs. Given that we already know what the equation looks like, we can extrapolate from this that this is in fact a reflection in the x-axis. I did want to mention that typically when we're working on equations in terms of x, in order to represent the reflection in the x-axis, we will replace y with -y. So if I start with that initial equation of y equals x squared minus 4x plus 5, and I replace the y on the left side with -y, you'll notice that now in order to isolate my y, I'll be multiplying both sides through by -1. This gives us y equals -x squared plus 4x minus 5, which is equivalent to the graph that we had done in red on the right. Let's remind ourselves one more time. The reflections in the x-axis, sometimes called vertical reflections, take the function y equals f of x and transform it to y equals -f of x. F of x represents the output value or the height of the graph, so we have made the height negative. Remind yourself that the x-axis is sometimes called the line y equals 0. We often see the letter y there and think y-axis, but in fact the line y equals 0 is the collection of all points having a height of 0, and it's therefore a horizontal line. The mapping notation or mapping rule that we use for this transformation is that xy becomes x and negative y. So all points with a height of 0, which is to say all the points on the x-axis, will be invariant. They do not change on this transformation. And finally, if we want to affect the equation in terms of x, we simply replace y with -1, which leads to a next step of multiplying both sides through by -1 in order to re-isolate our positive y value. If you're feeling confident with vertical reflections, ones in the x-axis, you'll probably have no trouble with horizontal reflections, ones which are in the y-axis. Basically, instead of reflecting in the line y equals 0, we reflect in the line x equals 0. So instead of making the y coordinates change from positive to negative or vice versa, we do that to the x coordinates. Here we're given the graph of f of x equals square root of x minus 2, and we're asked to sketch its image after a reflection in the y-axis. So our mirror is vertical, our reflection is horizontal. This makes sense. If you picture a mirror on your wall at home, your image appears at a different horizontal position from you. It doesn't appear to be higher or lower than you. So maybe before you advance the animation, pause and try and draw the reflection here. So again, let's track a few points. The point 9 and 1 became -9 and 1. The point 4 and 0 became -4 and 0. And the point 1 and -1 became -1 and -1. You'll notice that our y-intercept of 0 and -2 remains unchanged. That's because the x-coordinate is 0, and as we change its sign, it has no effect. So again, we will describe the effect of a horizontal reflection as one which makes all the x-coordinates negative. Otherwise said, it multiplies all x-coordinates by -1. The mapping rule is that the point xy becomes -x and y. Something that's a little bit trickier to understand at times is how this appears in the equation in terms of x. People often struggle when replacing x with -x because they want to introduce unnecessary brackets or fix the order of operations somehow. Now, this example doesn't have any value added or subtracted with x underneath the square root sign, but it'll come. So what we've done here is we've shown the graph of root x minus 2 and root of -x minus 2. Now, don't get hung up on the fact that there's a negative sign under square root. Many people will say, well, you can't take the square root of negative, which is true. But of course, if x itself is negative, then you have the negative version of a negative value, which makes the radicand, the number under the square root sign, positive, and therefore satisfies the restrictions for the square root. So what we do see is then that the effect is all points have been reflected over the y-axis and have changed their x-coordinate. Earlier we talked about how a reflection in the x-axis meant that we put the negative sign out in front of f. Here, when we're reflecting in the y-axis, we'll actually replace the x in the brackets of f of x with the negative x. And again, the effect on the equation in terms of x is therefore to make the actual x be written as -x. Exploration number 5 is another chance to work with a reflection on a piecewise function. This is actually the same piecewise function from exploration 2, but this time we'll reflect it in the y-axis. So rather than changing the y-coordinates from positive to negative and vice versa, we'll change the x-coordinates from positive to negative and vice versa. Take a second to map the 5 indicated points on the graph to their new locations. Notice that the point that used to be at -5, -3 is now at +5, -3. The x-coordinate has changed its sign, while the y-coordinate has maintained the same sign. Similarly, the point that was originally at 3 and +2 is now at -3 and +2. The point that did not change is our y-intercept because it was located on the y-axis, which is the axis of reflection. So our mapping rule for a reflection over the y-axis, also called the line x = 0, is that all x-coordinates change their sign. So we write xy becomes -xy. In this case, the y-intercept was found at 0 and -1, and we can tell that that's the only point that didn't change under this transformation, so it will be our invariant point. Now, I want to highlight that if ever you had a point on the original graph that, when reflected, had its transformed point land on another place that had been on the original graph, that's not considered invariant. Invariant doesn't mean it goes to another point that was there before. It means it literally did not move. It did not change its position in any way. Sometimes that happens in certain examples and people get confused. So important to note, it must have not changed its own position at all. In order for exploration number 6 to be helpful, it's critically important that we understand two things. One, what we're trying to do here, and two, what rules will constrain us. So just like in exploration number 3, we're given the quadratic function y = x² - 4x + 5. We're going to graph it in our calculator and find the coordinates of the vertex using, in this case, second calc minimum. Now, in the second bullet, we're given y2 equals a bracketed -x² - 4 times a bracketed -x + 5. And it's really important to understand that this means we've replaced x with -x, and that replacement should indicate a reflection over the y-axis, so a horizontal one. However, this will only work for us if we properly bracket that first -x that is squared. Because if we don't bracket that -x, that will actually alter the order of operations. I'll elaborate on that a little bit more as we go through this. For now, let's sketch y1 and find its coordinates. So y1 is the blue graph that we see, and so it has the vertex at +2 and +1. The next graph of y2 is the green one. We see its vertex at -2 and +1. We can tell then that the x-coordinate has changed, and judging from this and what we see, we can tell that this is a reflection over the y-axis. Now, if we had not bracketed that -x², let's just say this. -x² means -x times -x. That becomes +x². But without the bracket, it would actually be as though we had x² times -1. And that is a reflection in the x-axis and would change the vertical component of our graph, making this completely different. So very, very, very important there that we input with the bracketed -x. Though we've labeled exploration 7 as a summary of the reflections, the algebraic work in this will make it one of the most important slides in this section. So here, we are shown on the left a vertical reflection, which is to say a reflection in the x-axis, and on the right a horizontal reflection, which is one in the y-axis. We're going to talk about the mapping rules, name the invariant points, and then show how we write the functions both in terms of f of x and also in terms of x. So let's start on the left. Here, when we reflect over the line y = 0, all points have their heights changed from positive to negative or vice versa. This means any points that have a height of 0, which will be found on the x-axis, do not change and are labeled as invariant points. We write this in terms of f of x by saying y equals negative f of x, because it is the height or output value that has been made negative. Let's have a look at the equation given for f of x in blue, which is f of x equals x minus 3 squared minus 1. In order to transform this equation, we would have to perform a replacement. At the bottom here, I've shown the replacement where y was replaced with negative y. As a next step, when we multiply both sides through by negative 1, we arrive at what was shown on the line at the top there, y equals negative, and then a bracketed right side of the equation. The detail I need you to notice here is that the negative 1 becomes a positive 1. So it's not just the negative sign in front of the bracket. It's also distributing that negative 1, or that negative sign that doesn't have a 1 written, all the way to the negative 1 at the end there. We typically call that the k value. In Math 20, you may have seen it written as a q value. Now, when we look at the horizontal reflection, which is the one in the y-axis, our mapping rule will be different. Here we'll see that the height of each, here we'll see that the x-coordinate of each point was changed from positive to negative, meaning the invariant points are found on the y-axis. We write this in terms of f of x by putting the negative sign inside the bracket with the x. Again, it is the x-coordinate being changed, not the y-coordinate. In this case, because we're writing this in vertex form, we'll show this transformation by simply replacing the x with a negative x. But the next step can fool people a little bit. When we factor out the negative 1 from the negative x and the negative 3, it remains in a bracket still affected by that exponent of 2. This means that the negative sign, or the negative 1 out front, is squared, as is the x plus 3. When we square negative 1, it becomes positive 1. And so this equation becomes y equals x plus 3 squared minus 1. So important to notice, comparing the vertical and horizontal reflection, that in the left case, that negative 1 at the end became a positive 1 because we had a vertical change, and that k value represents a vertical transformation initially. In the right example, we did not have a vertical transformation, and therefore the negative 1 was not changed. Only the inside of the bracket was. Hopefully, the explorations we've been through together have given you the confidence you need to complete this class example. You're given the same graph twice, and in the first case, you'll be asked to sketch the graph of y equals negative f of x. Which reflection was that? Was that the reflection in the x-axis or the y-axis? Try to recall, or check your notes, and then draw the appropriate reflected image. Indicate the mapping rule, and identify the invariant points. On the right, try that for y equals f of negative x. Take some time to do this before clicking through the animations. How'd you do? I want to highlight that here I described the reflection as being in the line y equals 0. You could have also said in the x-axis. If you wrote that it was a vertical reflection, that's understood for your homework, but wouldn't be appropriate for a formal exam. You do have to indicate the axis of reflection. Notice also that every single point had its y-coordinate changed without changing its x-coordinate. That's why the mapping rule shows xy becoming x and negative y. The x is not changed, only the y is. Our invariant points here were the 2 points on the x-axis, which were 1 and 0, and 4 and 0. Those x-intercepts will be the only invariant points under this reflection. Try the right side. So now we see what happens when we reflect in the y-axis, or as I've written here, the line x equals 0. Remember, writing horizontal reflection would not be precise enough for a formal exam. Our mapping rule is the points x, y become negative x and y. So now only our x value changes, not our y value. For this reason, the invariant point of 0, 2, our y-intercept, is the only one that is not changed because its x-coordinate was 0, which is the only value not affected by changing the sign. How'd you do? Conceptually, the idea of a reflection isn't really that complicated, and so students usually do very well when working with them graphically. However, when trying to transform equations that have been reflected, it's a bit more nuanced and sometimes little errors can be made. Let's have a look here at the function f of x equals x squared plus 8x plus 12, so another quadratic function, and transform it in one case with a vertical reflection, so over the x-axis, and in the other through a horizontal reflection, and see how their equations turn out differently. So when we reflect over the line y equals 0, which is the x-axis, we write the transformation in terms of f as negative f of x. This means that if x squared plus 8x plus 12 is equal to f of x, since we made f of x negative, we'll be making all of this negative. So we put a negative sign out in front of some brackets and then distribute it through. The other way to think of this is that we made a substitution of y with negative y, or sorry, a replacement of y with negative y, and then multiplied through by negative 1, giving us that same result. If, however, our reflection is over the line x equals 0, which is the y-axis, in this case, we write the transformed function in terms of f of x as y equals f of negative x, because it is the x-coordinate that we're making negative. So now, when we want to write the equation in terms of x, we have to replace each instance of x with negative x. Be very careful when you do this. It's so important those negative x's are bracketed. In the case of the 8x term, it will change from positive to negative. But in the case of the x squared term, what was originally x squared, because it is a negative x squared, the negative sign will be effectively canceled out as negative x times negative x goes back to being positive. This gives us a final form of y equals positive x squared minus 8x plus 12. Now that we've determined our transformed equations, it's worth putting them into our graphing calculator to confirm that we've correctly associated them with the vertical or horizontal reflection. You can see in the left case that when I put negative out front of a bracketed x squared plus 8x plus 12, I do in fact show the vertical reflection. And when I replace each instance of x with negative x, as in the right case, we do get that reflection over the y-axis. This is a continuation of the previous slide. In the left graph, you should draw the transformed image of the parabola after being reflected in the x-axis. And in the right graph, you should draw the transformed image after being reflected in the y-axis. Do this, then try to determine the coordinates of the invariant point or points, as well as the domain and the range for your transformed graph. Notice in this left graph that under the reflection in the x-axis, our mapping rule shows that xy becomes x and negative y. So we've changed the sign of every y-coordinate. This means that points on the x-axis did not change. So our x-intercepts that happened at negative 6 and negative 2 were unchanged. All parabolas, whether opening upward or downward, will have a domain of all real numbers. The range is limited by the maximum height. So in the case of the green graph, our highest height is 4. So our range will be all values of y such that y is less than or equal to 4 and is an element of the real numbers. In the right case, we see that our mapping rule is that xy becomes negative xy. So all the x coordinates have been changed from positive to negative, or in this case, negative to positive. The only invariant point here will be our y-intercept that happened at 0 and 12. Again, the domain of the transformed function, because it's still a parabola, will be all real numbers. This means there's been no change to the domain after the transformation. Also, because our transformation was a horizontal one, which is to say the horizontal reflection in the y-axis, we haven't changed the range from the original graph. So where it originally was all values of y greater than or equal to negative 4, it is still that same range. Sometimes, as we work with transformations, we find some particularly interesting cases. Here, let's take the base parabola of f of x equals x squared and try a reflection over the x-axis and then later over the y-axis. When we reflect this over the x-axis, we get a graph in which all points have changed their y-coordinate from positive to negative, except of course for the vertex at 0, 0. That is the one invariant point. We've seen this before. This is nothing surprising. But what will happen when we reflect the original blue graph over the y-axis? In terms of the equation, this means we're replacing x with negative x. But because it's a bracketed negative x, when we square it, we arrive back at our original equation. This means that both the original and transformed function have the same graph. This can be a little bit confusing at times, because it appears as though the transformation has not taken place, when in fact, all points except one have moved. They've simply moved to a place that was already occupied before. An important note here is that there is still only one invariant point. The vertex is the only point who did not move from its location. All other points moved, it's just that they moved to a point that had previously been a point. Another interesting case is when we consider our base reciprocal function, y equals 1 over x. And we'll also look here at our base cubic function, y equals x cubed. What happens when we reflect these graphs over the x-axis or the y-axis? Interestingly, when we look at their equations, whether we replace the entire equation or make the entire equation negative or simply replace the x with a negative x, we end up with the same transformed function and original function in both cases of the reciprocal and the cubic. This means when we look at their transformed graphs, we won't be able to distinguish which reflection took place. Here we see on the left that the green graph, which is transformed, may have been a reflection of the blue graph in the x-axis or may have been in the y-axis. Looking at the cubic, we see the same thing. Here, our green graph, the transformed one, may have been a reflection in the x-axis or the y-axis. This one has an invariant point at the vertex 0 and 0. The graph on the left of the reciprocal had no invariant points. Another interesting note is that if we applied both a vertical and a horizontal reflection, they would actually cancel each other out because they are performing the same transformation in effect. So far, we've talked about reflections over the x-axis and reflections over the y-axis. In this next class example, we're going to apply each one to the graph of a radical function. Now, I want to look ahead to part A, where it's going to ask us whether it matters in which order we apply these reflections. I want you to think about that as we work through this. First, let's just arbitrarily say that we will reflect over the x-axis first and then the y-axis. Try it yourself before clicking through the animations. So, in our reflection over the x-axis, we see that because there were no points on the x-axis, which is the axis of reflection, there will be no invariant points. Every point's y-coordinate has been changed from positive to negative. In our reflection over the y-axis, the horizontal one, we've changed the x-coordinates from being positive to negative. Again, no point was on the axis of reflection, so there are no invariant points. Now, does it matter whether we reflect over the x-axis first or the y-axis first? The answer here is no, and there's a really important reason. I want you to understand that when we reflect over the x-axis, that's our vertical reflection, it is a vertical transformation. It has no effect on the x-coordinates or the domain of the graph. And when we then reflect over the y-axis, the opposite is true. It's a purely horizontal transformation. So if you think of this, the graph has a domain and the graph has a range. And when we affect one without affecting the other, why would it matter in which order we do so? So whatever's going to happen to the domain is going to happen whether we do it first or second. And whatever's going to happen to the range is going to happen whether we do it first or second. It is important in this course to remember the order when treating multiple transformations on the domain or multiple on the range. For example, to have a horizontal translation and a horizontal reflection, it is critical to treat one before the other, depending on the circumstance. But in the case of a vertical transformation and a horizontal transformation, it should not matter in which order we apply them. Now, in order to state our transformed equation, we're going to see both happen to the equation. So we're going to replace x with negative x, and at the same time, we're going to replace that y with negative y, and then multiply the entire equation through by negative 1. So you'll notice here that the x under the radical sign has a negative coefficient now, and that there's also a negative not only in front of the radical, but in front of a bracket that includes the radical and that plus 1. When we simplify this, that negative out in front multiplies to the positive 1 to make it a negative 1. It cannot multiply into the radical for reasons having to do with how square roots interact with their coefficients. You know, you couldn't take a negative 1 in the coefficient and distribute that into the root for a square root. Excuse me, into the radicand for a square root. So looking at our green transformed graph, we can see that the domain is the opposite of what it was initially. It used to be all values greater than positive 3. Now that we've reflected it, it's all values less than or equal to negative 3. Similarly, our original range was all values greater than or equal to positive 1. Now that we've reflected it, it is all values less than or equal to negative 1. I hope that made sense. Kind of a tricky idea about order mattering or not, because in some cases it does and it's very important, but here it wouldn't make a difference.